All right, good afternoon. I want to thank you for coming to the first of our 75th anniversary Stillwell Memorial Lectures. I'm very pleased to introduce to you Professor Hanspeter Schaub from University of Colorado at Boulder, where he is the Glenn L. Murphy Chair of Engineering in the Smead Aerospace Engineering Sciences Department. He is the director of the Autonomous Vehicle Systems Lab, where he has a lot of graduate students. He is the author of a very well-known textbook on analytical mechanics of space systems, which is an excellent book.
Thanks, appreciate it.
And is an AAS and AIAA fellow, and he is currently the editor-in-chief of the Journal of Spacecraft and Rockets. So please join me in welcoming Professor Schaub.
Okay. Thanks. Thank you very much for the invitation, Zach, to come here to beautiful campus. I got to experience some rather interesting rainfall yesterday flying in here, but today is a gorgeous day. This is really quite something. Also, it's been a wonderful day visiting with faculty and research labs. There's so many exciting things happening there. With these visits, this is always a chance to kind of show a little bit what we're doing as well. And so my talk here will be talking less about math and more about what we do with math and how we make this, especially with very much a space-centric focus. How do you get this actually out to be used? How do we get it to be shared? And what are some of the exciting capabilities that we have? If we give talks, our department had always wanted to give a quick synopsis of who are we ourselves. I'll do this very briefly. We're really a well-funded NASA department, a lot of projects, a lot of missions being run from Boulder there. We've got about 850 undergraduates and about 450-ish graduate students, of which about half, so well over 200 are PhD students. That's the size of our graduate program there. Well over 40 faculty, a lot of associated researchers, instructors, and things that are happening there. So a very large department. What makes us a little bit different is our department's broken up into 4 different focus areas. And you have the classic spacecraft systems engineering, which is really housing structures, fluids, kind of combined, and controls. Then we have the astrodynamics and satellite navigation that has all the astro people and also GPS researchers in there. And then the two of them, bioastronautics is about sustaining life in space. So a lot about doing flight experiments with humans and plant life and all those kind of things. And then also remote sensing. This is an Aerospace Engineering Sciences department. So about a third of our faculty are actually scientists. And it makes interesting collaborations with us that we get to work directly with the people who need the science, the sensors, and how do we use drones or spacecraft to look at Earth, to look at space, and do everything simultaneously. So that's kind of the breakdown. The big news from our end is we actually got a brand new building. Since I've been at Boulder, they've always talked about, yeah, we're going to get some expansion, we get a new building, and you go, yeah, I'll believe that when I see it. Well, it's actually built. We actually moved into it. And when I say built, I should say it's mostly built. This last week, they're still jackhammering right above my office, installing some new sensors for the remote sensing people. But beyond that, we're very close to being done. So it's a really cool modern building. It's going to make it much easier for research collaborations, all these big classrooms. This classroom, for example, can house 220 students. It doesn't look like it, but you're only 6 levels deep. So you as a professor, you can walk around, navigate, talk, and if there's a discussion coming up, I can walk to that side and actually engage with that person versus having to go, no, 5th row from the top, that kind of stuff. So I'm really excited to teach these large classes in there that we have these days. So that's my department. Now my lab, the Autonomous Vehicle Systems Lab. I will give you a brief summary of some other things we're known for, just to give you a highlight. I've currently got about 16 PhDs. I've graduated a whole ton of them. There's lots of research that's going on here. There's no way I can talk about everything. But I did want to bring in a few highlights. One of them, the things I'm known for, is charged astrodynamics, which deals with using basically charge emission, electron guns, ion guns. You can emit it from one spacecraft onto another, create a negative field, you make yourself positive, and this creates an attractive force. We call this the electrostatic tractor, like Star Trek tractor beams, and you can push or pull and repel things. This comes from the special features of gravity there, the second side, where they talked about debris solutions, and this was one of the things they looked at and wanted to do some things. But as in classic Hollywood, they made this little movie from the stuff. They got this physics right, but then of course, where do they tow the debris? for some reason into a polar orbit into the sunset. I think the key thing was they wanted to go into the sunset for Hollywood effects. But it was cool to see it highlighted in that movie. We do experiments in there on charging as well. So I've got some physics students working in my group on charged astrodynamics. Space debris is another. A lot of that work that we're focusing on is at GEO. And while many people focus at LEO, we've been looking at the GEO ring, where the stationary ones are operating satellites. Everything else is meter size or larger trash flying around. And we've been doing conjunction analysis and how close things get. And Air Force gets nervous when things get within a few hundred kilometers, but we're showing there's some regions where things come in daily within a few tens of kilometers. And then there's almost like space weather, there's debris weather patterns that emerge, and we can predict all that. So that was something that's a lot of work's been going on. So my group does astrodynamics, the motion of, dynamics control of man-made objects. I got to work on the Cicero mission, which was really exciting, with the Laboratory for Atmospheric and Space Physics. And this was a 2-spacecraft GPS occultation. What was interesting is it wasn't funded by NASA, it wasn't funded by Air Force, but by a former JPL leading research scientist on GPS who drummed up enough venture capital to get this started, and they hired us to get this all going. So it was very different not having NASA bureaucracies or Air Force bureaucracies to deal with. It didn't quite fly at the end. The business plan kind of fell apart, but we went through very far into the design that they're still using there at LASP. But from here, this other opportunity came along called the Emirates Mars mission, for which CU is the official education partner. So we're working very closely with them on the science development, but also on the spacecraft development. And we've got, step one is not engineering. Step one is legal export control. So I have to get all the export licenses. But now that's all fully set up, a building that we can team with, collaborate with, and work. And this is really a mission that's launching next July, and it's a typical large Mars spacecraft, about 3 meters tall, about a ton, with all the fuel on it. That's going to go out there, and then it's going to be a high elliptic orbit and do a whole variety of upper atmosphere sensing, infrared, visual light images, high resolution images, things that they want to do there for atmospheric sciences. So that's what we're involved in. This led to what I'm talking about today with this astrodynamic software. All the software that you see developed is really supported and being developed specifically to help with this mission, which is exciting. And so I have to give credit for them. So let's talk about spacecraft simulation. I mean, most here are familiar with how to simulate dynamical system. You've got some ordinary or partial differential equations, you have to write a lot of code, or maybe you have packages that you can run, but then these black box solutions are kind of challenging because they don't do exactly what you need. So I want to go through some of these challenges. If you look at a spacecraft, just the physics, people still write whole PhDs on just how to do solar radiation pressure. That was one of my recent PhDs from last May. One of my students, I should say. Atmospheric drag, modeling those things. Fuel slosh is hugely complicated. Orbits, 2 bodies, we know, conic section. 3 bodies, how hard could it be, right? People are still writing PhDs just on the 3-body problem, on trajectory optimization. So these are big fields of research, and if you want to blend them all of a sudden, then this might be written in Fortran, this might be written in C, this might be written in C#, and how do you, as a graduate student, you always get those dreaded words from your advisor. Could you just, merge code from 2 years ago with this stuff? And it's like ramming 2 Titanics into each other, expecting this is to be a better ship, but it doesn't, it just sinks. And you build it from scratch, right? I mean, that's ultimately what it's about. More than the physics, spacecraft also contain a lot of sensors. So you have to model these sensors, star trackers, gyro, thrusters, actuators. And I was giving this talk at Ball Aerospace, and there was one of the scientists who had some of these optical sensors. Like, oh yeah, I've got a great simulation for this, but it doesn't work with anything else. I can't put in orbits, I can't prescribe attitudes, I can just model the physics of it. Could this be used? I go, yeah, in this format, it could be. But people put huge amounts of work into these things in separate code bases. And of course, the really important part is all the code. Spacecraft are not just hardware and sensors and fuel and everything, but some logic that determines fire now, turn on the thruster, turn to this direction, And that's all the algorithm. That's an integrated part. So we want to simulate all this in a very cohesive way. And if you're doing spacecraft, there's a lot of monolithic solutions. So my exposure to the Cicero program was very classical. You had this big program that simulated something and did a lot of cool stuff, but it wasn't very flexible. If I have to have different design parameters, I'd have to go into code and change code and recompile. And every time you touch code and recompile, people are worried about what did you break, what unknown unknowns are there out there. And so that was a big challenge. And so a big question in space, we're super conservative. All right, you're flying to Mars, you get this opportunity once. Or think of the Pluto mission. People built that spacecraft, had a whole life. Now on retirement, they finally arrived. You're not going to put something high risk on there. You want something that's so simple, and even if it's more expensive, you're going to fly it. So that's a problem. And we have to think about everything we do is how do we verify, validate, but we want to reuse code. That's critical for bringing the costs down. And we want to also reduce the development cost to get into place with new stuff and be able to, this is a big thing to me, continually improve. It's always embarrassing when I'm looking at there are different solutions that are flying, and they're still flying code that is decades old. Chatting with JPL, it's an amazing work that they do. I'm supporting one mission, and this one colleague was saying, we're supporting 30 simultaneously, and every group has their own design decisions and what they want to fly. And some of this code that we have to support is like literally 30 years old that somebody wrote figuring this will have a shelf life of 5 years. Surely by then, Josh will have made newer stuff. Well, that surely never happened. And now they're still supporting this stuff and trying to figure out how to integrate it into new things. So there's all this legacy that can really hamper you. And the exciting news is space is growing up. There's huge opportunities where people are flying, mega constellations and all kinds of crazy, asteroid mining and other things they want to get into. We can't do that flying like we did Apollo 11. So how do we get better? And this to me also came fundamentally with this slide is what are we going to do with this code? Academia is famous for this ivory tower concept. The biggest product we have is the papers we publish, right? That's often what gets you awards, what gets you tenure, how many papers. And we can always yell at the industry, you guys are idiots, why aren't you using my stuff? I published this 10 years ago. But good grief, go read your papers from 10 years ago, Do you understand what you were talking about? What was the notation? What was the framework? How did you initialize this? What are the subtleties of the code and algorithm to implement this filter? That is really difficult. So you can write this stuff, and then a few people in the world may use it, but the most likely thing industry will do is forget the paper, I'm going to hire you, right? And they get our graduates, and they help implement it. And this works. Now you go work at JPL, you get some things done. And so we do a lot of papers, great ideas and concepts, and industry, research labs build all these different systems. And we need to bridge this in a more effective way. And so for me, working with LASP has really been transformative for my career in a way that I get to work with an actual mission operation. They build, design, breathe spacecraft every day, and I'm doing the academic side. And we've been trying to come up with a methodology that we can do rigorous academics and move it on into production all at the same time. And this is where Basilisk has been very helpful. Right now, there are several different groups that are using it. It's probably, at least it's open. I can't control, I don't know who's all downloaded it, but I know from ones I hear from, and there's at least 2 industries that are using it very heavily. And there's about 5 or 6 different research groups, academic, who are using it. Some of them are already using it on small sats and flying it before I even knew. So this is Basilisk. We made a logo. It's a lizard, long fingers. It's a lizard that can walk so fast, it can actually walk on water. It doesn't break the van der Waals forces. So that was a name that we came up with. Zach was asking me earlier how we came up with this name. The other influence is, I'm from Switzerland. I grew up near Basel, and Basilisk is actually the mascot, the logo of Basel. So there's a little Swiss connection in here. And the other thing is we consciously didn't want to do an acronym or some contrived, this means, ballistic, astrodynamics, something. It's a name. Let's get past the 70s and 80s technology and ideas. It should be modern. So we gave it a name. Turns out unbeknownst to me, JPL is doing the same thing these days. They're just naming things after animals with their software. So we're in good thing. So what is Basilisk? We wanted to do something that's away from the monolithic architecture and how you integrate stuff. So we now have something that's highly modular. Now, many things are modular. If you did object-oriented programming, that's modular. Many different software solutions claim to be modular, and some of them actually are, some of them are kinda, but many of them are a real pain to use as well. I can tell you privately which. But what we're trying to do is have something to where when you code this, I literally just say, look, okay, give me a spacecraft, and that's a spacecraft object. I want to evaluate it every 1/10 of a second. Add a panel that's flexible. Add some fuel slosh. I'm not adding a single line of code into how evaluate these differential equations. That was a big challenge we had to deal with. Many code bases out there break some assumptions. Yes, wheels impact spacecraft, but spacecraft also impact wheel dynamics, and that's often dropped because it makes it really hard in this object-oriented way to have this back coupling. So we had to build new stuff. So this allows us to have modules in C++. I can write modules in C, because in flight algorithms, we typically still fly C, not C++. But we gave it object-like behavior, so we had to write our own interface around it. And then Python, using Swig, an open source library, we can wrap these in a way that you can call it from Python. So to run a Basilisk sim, if you're using existing technology, You just have to run Python, create this, pull in Basilisk, create this, add this, run the stack, and you get everything included. That means no code writing is important. There's many packages that'll auto-generate code, which is very powerful. They can do way more complex dynamics. Robotic landers bouncing off an asteroid in a weird gravity field. I can't do that. But the stuff I can do really well, and you don't have to worry about verification validation. It's been done once already. We will also talk a little bit about the visualization that comes with it and some of the basic capabilities. It's really fast. Our goal was 365 speed up, so we could do one mission year in a day. And I'm not talking with 10-minute orbits integration time steps. I'm talking like 10 hertz attitude integration, so we can do the full on. And we're well exceeding that. Now, if I crank up some of the fidelities, I can always bring it to its knees, naturally. But with pretty complex stuff, with some panels, some flexing, 2 to 10 hertz control loops running, we can get 700 to 1000x speed ups despite these Python interface layers, which is good. It is ISC open source license, which is essentially the same as the MIT license. You can do anything you wish. There's no give back clause. The one thing you can't do is sue me, all right? But otherwise you can do it, use it, commercialize it, whatever. But also hopefully give back. So this was running a single sim. We've also shown how you can break it up into multiple components across computer. Here, Mars, she was running it on the Raspberry Pi. It's a popular platform for small sats, illustrating how you can communicate and have essentially a hardware-in-the-loop simulation that you're doing here. And I'll talk a little bit more at the end of the talk about some stuff. What does these things look like? When you run it in our software, we've got task groups. This could be like the spacecraft. You've got a task. This rate gyro needs to be updated every 10th of a second. Other things might have to be updated, your dynamics every 2 seconds, or depends on what's happening. You can stack that all together. And these messages will be interfaced with each other naturally. Then you have other task groups which might be running things like your flight algorithms. So we can attach flight algorithms to the spacecraft, and then this one will have particular behaviors. And you can run different stacks of modules there too. This really creates a high level of interoperability, and it's thanks to this message passing interface. This thing took me some while to get my head around it because I'm used to classical engineering. You have MATLAB, you have some other functions, C. Everything's programmed to function. You give things structures or other information, then you operate on it, which has worked for years. With the message passing interface, you create these messages that you have to develop. There has to be a standard, and then you read it in, then you process on it, then you spit it out again, and something else has to read it in again. And why this is handy is you can have one module that figures out, I'm my orbit propagator, this is where my states are, it spits out a message. And then other modules read that message, create outputs that say, well, if you're there, your navigation says you should be aiming left, and the control picks it in, going, I'm not aiming left, this is my tracking error, and then it interoperates. What's nice too from a collaboration perspective, if somebody comes up and says, you know what, this module here, I've got a better idea. I want to throw something different in it. I can just take out that one module without recompiling code, just plug in the new module and test it out. And now we've been using that in the mission, and fairly late in the game, we really trust this software at this point that we can go, and yep, that new filter is going to work brilliantly and do this and run all the performance tests we have to. But this to me is also nice because the relationship I keep throwing, if you haven't done much with messaging system, think of what your smartphone, like if you have iMessage or Facebook Message or Google Talk or something, all these different messaging apps we're used to, it doesn't matter which platform you start out from. You can start on your smartphone, switch over to a tablet, go to a computer, switch back again. The message file is used. There's a common API, an interface protocol that tells you how to communicate. That's what we need for our space stuff. You cannot have one group saying, hey, we're doing attitude and quaternions, and actually the scalar is the last part. Next one goes, yes, we're using quaternions, but the scalar is the first element. And the third one goes, no, we're using Rodriguez parameters. It's just going to be mayhem, right? So if you have some standard, now you can start to interoperate. And at the end, it doesn't matter which ones we use. You can always translate into whatever you need it to be. And that's what we're doing. And this also allows us now where we could be developing stuff, and then I know Australia, New South Wales down there, they are looking at some modules, and they can share us their code, and we can interface it in our code very, very readily. And again, I'm doing this also with several other mission concepts and industry. These messages are essentially C++ just structures. You define what it is. It has the maximum thrust, the thrust factor, how much force the thruster is producing, in what direction the force is going. All these things are defined in here. And these are written out and read in through the system. The importance is having some standard of what these are. And we can do those. They're also double buffered. But it is not thread safe, so this single simulation is not multi-threaded yet at this point. We're looking at modifying the messaging system to try to move towards being thread safe, but that's a big computer science task. So a general simulation, we can now stamp out equations of motion, wheels, thrusters, different things, run this in a pretty complex way, and do a bunch of things. One thing I want to highlight, equations of motion. This is the one thing where we tried hard to use a messaging system, but finally had to just go, this is not working because of the feedback loops. That the wheels affect spacecraft, but spacecraft also affect wheels. These things are fully coupled, nonlinear, differential equations, and we didn't want to truncate. A lot of codes truncate these things or assume that's small, and they're right. For mission analysis, it's perfectly fine. But for academic research, if I get a wiggle in my energy state, I want to know it's due to something, not just due to some coupling that I broke, Because I want to debug complicated multi-body dynamics. So we actually created our own state engine and a way of writing and solving these equations of motion that another PhD of mine just published that allows us to do this in a very modular way and closed form way. It doesn't require any equation solving. And it's very fast, actually. And so he's done that. I'll show you some examples. Beyond space, we also have space environments, and our space scientists in our department are quite excited about this because they often have tasks where they have this new atmospheric density model and they want to compare it to others, and these are all written in different code bases. How do you integrate this? So we, this summer, actually got neutral density. If you do that, we used EMSIS, which is a very popular NASA model. We've got some other density models we'd like to include now, and you can easily do compare and contrast. You can add to a spacecraft 2 different densities at different altitudes. You can mix and match to your heart's delight. So we hope to provide more and more tools where we're also wrapping this code around science, environmental aspects, and bringing it in. So you, as an end user, if this is not your specialty, because you do optimization, you can turn it on and just use it, which will be very nice. And the scientists will use it as well. So that's ongoing work. Multiprocessing, like I said, it's single-threaded right now, but we're using some Python libraries to do Monte Carlo, which is essentially sensitivity analysis. You have to do a lot of what-ifs. That's where we are using multi-core processing. So each core can take over a single Basilisk simulation, and if you've got 8 cores, you get an 8x speed up right away. So that's really nice. It also does data retention, so if one of the runs fails, it doesn't bring down the whole system, just that one thread dies, and you know which one died, and then you can run it again. This is a nice picture, but the history behind it is, anybody here use matplotlib before? Python? Several of you. Any of you plotted like 200 gigabytes of data in matplotlib before? Have you tried to plot something large? You should, just for kicks and grins, but do it overnight, because it's going to take a long time. We used to plot like 5 gigabyte, 10 gigabytes of data, and it would literally take an hour or two just to finish the one plot. Then you go, oh, the axes are off. Redo it again. Go back to class, come back, oh, this is off. This is where we found some computer scientists came in and said, hey, there's things called data shaders and holoviews in Python that you can do it. They built this tree topology of the data structure so they can quickly rip through it and figure out which one of all these massive data sets actually contributes to this pixel, and which one, once it's covered, it's covered. So we can rapidly now plot this in 20, 30 seconds. That used to take hours in matplotlib. And you can still dynamically zoom in, zoom out. So this is a super powerful tool that we can build and use on top of Python with other stuff that's coming in. So that's been really handy. Verification, validation. When we write modules now, every one of my students is learning this, that if you just write a module, if you write any code, you should always test it. Of course, that makes sense, right? But you have to test it in a way that is unit testable. Python has something called PyTest. You run it and you set it up and it looks for certain types of files and it automatically executes them and makes sure that it gives you expected answers. There's no faults found and it got what you needed. This is how you can make sure a module that's a multiplier, you put in 2 times 4 should give you 8. Yes, I got the right answer. So every test has unit tests, and right now over almost 1,100 and something unit tests that we're running within it. There are also integrated tests, because you can have all the unit tests work, but your simulation breaks because the interfaces have changed. So we also have tests that integrate between them, and we're trying to make it more and more exhaustive as well. So that is running, and this gives us a lot of confidence, because otherwise if you code in teams, you're always adverse to going, do I really want to change this part? What about the other thing? What am I going to break that I never even thought of, right? As long as all the functionality is put in a way that it's testable in automatic manner, and we unit test this stuff every night in a continuous build server that we're hired, This gives us confidence that we can move much more aggressively. And I rely on this test to go, yep, I didn't break anything. So that's all built in. Documentation, always the least sexy part of any coding project. Who here enjoys writing documentation? Okay, you're hired. You have a job. Everybody else, you're fired. You're out of here. No, but really, this is super critical, because if you write code, this may make the most sense to you right now, but I can promise you a month from now, you've had who knows how many meetings or the project, you look at your stuff and going, why did I write it this case? You're not going to remember. And this gets harder with time. So we're trying to use what the open source community does. So we're using Doxygen, and we're trying to enhance this with other ways. But the code contains documentation, and it can generate HTML documentation of the classes, of the tutorials, and how to program. Is it complete? No. Documentation is always work in progress. But we're trying to be good citizens and let you, actually have documentation of the stuff. So now let's give me a few examples of where we've published work on this. I'll apologize in advance, there will be some equations coming up, but it's more for eye candy than anything. One of them is reaction wheels. So in Spacecraft, you have these flywheels, momentum wheels, whatever you want to call it. You apply a torque, you then get a counter torque on the spacecraft, and I can all of a sudden make myself rotate left or right, and that's good. And very simple devices. The problem with these also are, as they're spinning, if they're not perfectly balanced, you get this jitter that happens, and how do you model it? And so we wanted to incorporate that, and that was cool. But the jitters are typically done in a way such that you just apply an external torque on the spacecraft subject to the frequency of the wheel. It's a really popular model. It's highly successful. It's been good enough for mission design. But if you apply an external torque to mimic an internal imbalance, your momentum is going to be all off. Your energies are not going to behave the way they should be. And now you try to validate a complicated multi-body panel deployment dynamics and going, well, I think it's not going down to zero because of this effect. You don't know. So we actually developed equations of motion with fully static and dynamically imbalanced wheels and made much more math and implemented it for reaction wheels. We've got them for CMGs, which are gimbaled reaction wheels, and even some double gimbaled ones that a Japanese visiting scholar was working on too. So this is really complicated stuff you have to put in. As an example, these are your classic rigid body equations of motion subject to n number of balanced reaction wheels, and these are the motor torque equations that relate your wheel accelerations to the torques, subject to this coupling back with the spacecraft. This is what's dropped most of the implementations. So what we do now, if the imbalanced wheel, this simple equation becomes this massive equation down here, and this is the short form. This is the coordinate frame agnostic form. If you'd throw in all the frames, this would take well over a page to write. If you want to implement this, you'd have to code it up, make sure the I's and J's are correct, the frames, the notations, the details are all done. This could take you weeks. And now it's all coded up in a way that the dynamics engine can account for. If I add a wheel, I will know right away where the wheel is. I put it, it resolves the equations to find, and it can compute it in a computational, very efficient way. The biggest matrix we have to invert is just a 3x3 in our system. Typically, if you do a classic equations of motion approach, you have 3 translation, 3 attitude, 4 wheels, that's 3 plus 3 plus 4, so that's 6, that's 10 degrees of freedom. You have to invert a system mass matrix that's a 10 by 10. Your matrix inverse grows with n cubed, and that gets really big, really slow, very quickly. Here, the worst we have to do is 3 by 3 because we've analytically been able to back solve that relationship and how it all comes together. So that was wheels. Flexible panels, we're modeling as a hinged panels, like the first mode, or you may have deploying panels that actually do this. And he also, Cody solved this for us and put this together. And here the equations of motion are just shown for, because now as soon as you change the shape, your panel goes up and down, your center of mass moves, things get much more complicated. You have to track all this stuff. And so now even just moving the panel, you will have an impact on the center of mass translation, the rotation, and also the panel equations. So this is fully integrated into this stuff. Fuel slosh, this was fun. We got that built in where you have depletable mass, your fuel tank can go down, you have different fuel tank models on how the mass gets pressurized or moved around. But then the other challenge we wanted to play with is, if we're doing orbit insertion, you're firing fairly large thrusters, and orbit insertion on a planet is always scary. You get 20 minutes, that's when you have to fire. If your computer resets, you better hurry to get back in line and do it, because if you do it 10 minutes later, the mission's over, you've missed the planet. So we're looking at situations where we might have to very aggressively reorient with the primary engines to point back in line and fire them. And so we're curious what happens to the attitude motion while you're firing. While you're doing attitude tumbles and firing big thrusters, your thrusters pick up momentum of the spacecraft, translational and rotational. So you have to do these full Reynolds equations around the volume. It's an open dynamical system. But all of this, Paolo from Italy actually solved for us and put into Basilisk as well, into these equations. So now you don't have to solve them again. This is Patrick Keneally's recent work that we're doing with basically taking CAD models of a satellite and trying to compute solar radiation pressure. In deep space, this becomes one of the dominant disturbances. Even at GEO, if you're flying differential solar for formations, it's a big disturbance. And so you want to figure out how's the momentum buildup, how it affects trajectories. The MESSENGER mission is flying very close to the sun. They're using it on purpose, actually, to do attitude and translational control. But it takes them quite a few weeks to plan all these missions and get all the parameters just right. So we wanted to do it. Our motivation was too that with mission design, 1 week we had 2 panels, then it was 3, then it was back to 2, but 1 short, 1 big, and every time they ask us, what's the impact on everything? So we wanted a very fast way to evaluate this. There are other ways to do solar radiation pressure that are really fast with lookups, spherical harmonic expansions, but we wanted to bring in GPUs so we can bring in the full CAD model. This allows us to get a brute force answer where the CAD model could even be time varying. You could have flexing and deployments happening, and then compute the sun pressure. This is the faceted model where we're just doing a simplified where the sun is coming from. This is seeing the sun. Blue would see the sun if the antenna wasn't in the way. So that's shaded region, and green never had a chance to see the sun. That works really, really fast, but it doesn't account for sunlight bouncing off surfaces. The secondary reflections could be 20, 30% sometimes of the forces and torques. So you have to go to ray tracing. So Patrick also used stuff from the gaming industry and applied it here, where we're solving not just what's visually looking good, but proper fully resolved physics. This is with single bounce, double bounce, triple bounce. And this is applied to the OSIRIS-REx spacecraft. Oh no, wait, this is MRO, I think. This is MRO. I forget which one he had here. But that was kind of cool. This one is the OSIRIS-REx spacecraft. So this fall, if you talk about validation verification, we got invited to help them with OSIRIS-REx come up with a much better solar radiation pressure module, because they're now around the asteroid. They're trying to figure out what are all the non-conservative forces so we can learn the gravity of the asteroid that much better. And this is the single bounce, 2 bounces, and the differences in bounces. But he can resolve that, and he helped them identify all kinds of things to come up with a better model of these things. So that's work we're now integrating. A challenge of integrating in the open version is we're trying to support, Mac, Linux, and Windows. And with these things, you're running things on GPUs with very specialized libraries. And yeah, I see some smiles. So how do you make CMake cross-platform, integrate all this in a clean way? So that's something we're actually doing right now. The faceted hopefully will be out in the next few weeks. This one the ray tracing will take a little bit more effort to package up so it's easily testable and integrated in the open version. What we're doing for dynamics with this modularity also had a big impact on the actual algorithms. So the way we do our algorithms for this mission, we could have made a big monolithic thing, and a lot of people have that. Ball Aerospace, Lockheed, Boeing, they've been doing this for many, many years. They have existing flight code. And we keep telling them, you could take it and basically wrap a Basilisk module around it and just call the whole thing. Every algorithm ultimately has some inputs and it spits out some outputs, right? Some registers it controls with. So we wanted to take a little different approach since we're starting from scratch. And we made our algorithms actually highly modular. So we've been publishing some papers on how to take the attitude dynamics and how to break it up and chunk it up such that you get these very atomic behaviors that you can cascade together and make very complex behaviors happen with the spacecraft. And so we can have different guidance modules, estimation, different controls, different ways you pass it on to the thrusters. And we've been doing a few of this. This is one of the papers that came out with attitude control using a steering law. This is similar to how robotics do it often. They don't ask for forces and torques, they ask for speed commands. Robot, go forward, move right. It's really a speed command. And then the robot has a sub-servo system that implements the speeds. I tried a similar approach for spacecraft because it gave some nice behaviors where if I'm far off, I can guarantee a saturated rate. If you're really off, it's just going to go the best speed it can. It's like 1 degree, 2 degrees per second. Gives you well-defined behavior. And we did this. I did this all in Basilisk. I had existing modules. I had some things that were there. These were some new modules I created for this, and I was able to run it, connect this all together. And I wish I had this as a grad student, because late in the game, I decided to make my orbit not circular but elliptical, just because I wanted to highlight features of time-varying reference things. So it was a few lines of code, just make this now elliptical. And in Python, you can even spit out LaTeX code. You can spit out tables and figures and stuff that you need. So half the paper almost wrote itself once I rechanged that thing. This was performance plots. You get those nice exponential convergence on the nonlinear system, and subject to unmodeled torques. That's why the torques are not going to zero. It learns them enough and gets there. But that was a result of what we're running. Mar was doing some guidance. Guidance from Attitude, it tends to be very mission specific. You will find very few papers published just on this. But this is essentially, you're flying near Mars, you have a sensor platform, which for her was B2, I think this has all the sensors, and she wants this to skim across the planet and scan it in several different ways. This would take lots of waypoints to set up. And with her architecture, she's able to come up with these dynamic referencing, kind of atomic prototypes that you can cascade together, and with only 8 waypoints, she can do very complex, these asterisk-like scans across the planets. And everything else is fully autonomous. There's no human in the loop saying, now point here. You know, often these things are done with waypoint planning, with lots of different waypoints. We didn't need that in this case. So this was kind of a nice illustration of how to do software development in a very modular way. Don't have to, but you can. Now, up to now, Basilisk has just been running on one computer, using it for analysis. I want to figure out, will this mission work? You know, if I put this in, where do I go? How does my control perform? Am I stable? I'm going to have some issues. Now I want to talk about distributed version, where we're running it across a network. This will bring in something else called BlackLine. Again, it's not an acronym, it's just a BlackLine. It actually has the roots here. Scott, I have to blame Scott Pickett for this one. Anybody remember the old cartoon series Voltron? That's where the BlackLine came from. Okay, it was the master robot that kind of combined all this stuff, this old Japanese animation stuff. So yeah, it's good to have some fun. But that was Scott's idea. But what is this? With the distributed simulation, the task that was thrown at us from the mission is we have Basilisk that runs this great physics of what the environment, what the spacecraft, what the algorithms are doing. But now we have to execute these algorithms, and we want to do them on a separate computer. This could be a real hardware chip, like a flat sat we talked about earlier this morning with some of you guys. But in this case, we wanted to try a purely software version of it. So Lockheed has this great software called SoftSim, in-house proprietary, but it emulates the actual flight chip. So you're running a QEMU stack on a Linux box that it's emulating the instruction set that the flight processor will have, which is not the same thing as your Intel CPU will have. It's much reduced. So now you're running bit for bit the exact flight code on an emulation thing, but it only runs 90% speed. This thing is running like 1000x. And then they want us to tie in ground software. So this means our flight control room, we want to tie into simulation to test out. If I say go into science mode, does the spacecraft software really switch over? Ultimately, you test this on a flat sat, but with this soft sim capability, we can now do a lot of the basic testing first before we get to the flat sat to make sure the algorithm doesn't have sign errors, the communication talks properly. And then you go to the hardware to make sure the electronics, the power is handled correctly, everything else that you have to do. So to do this is pretty complex. And Mar and Patrick both, within a year, were able to create this thing called BlackLine, which is a router interface. It has, this is buzzwords from Patrick, dynamic discovery, the simulation, network topology. It synchronizes and starts, so you start this up, it brings up all the other interfaces and talks with it across the network. These are not on the same computers, not even necessarily the same building. And this software was never designed to be integrated into something else. So what we do is this thing is really the master control. Then you have what I call mini lines. These are these interfaces that you can send the message, and you can say, okay, they want telemetry. So this spacecraft simulation of this chip has telemetry. It gets the message, it knows where to put it. But then it sends back, go into this mode, this gets it. To go in that mode, it says send a signal to these thrusters to fire them. And it has all these complex interactions that have to happen. Synchronicity is critical, and this thing isn't even running real time. So what do we do here? We have to make sure, well, let me talk about I'll go to this slide first. That's what we had to do with soft sim and flat sat simulations. Where the research is, really, there's a lot in latent computing. The Amazon cloud is a fantastic platform. You can buy cheap supercomputing capability, right? But to move all your code to it might be really prohibitive. And there are some of these neutral density, space physics models that might require supercomputers, other things don't. So we would like to have interfaces that just, here's where you are, do your magic, give me back what the density is. What are the plasma parameters I have to deal about, whatever comes back. And I can keep everything else as is. This allows me to integrate other systems, other software, without moving everything to the Amazon cloud. So including distributed computing, GPUs, and I'll show you some results with visualization as well. There we go. So the key thing with synchronicity is a tick-tock cycle, a publish, subscribe step, where everything on a tick cycle, everything progresses, does its stuff. So the QEMU would then forward propagate, finish its thing. When it's finished, it's published, well, it gets out the stuff, gets the new things, gets one step forwards. And when it's done, it sends a talk cycle. So that's what they use in computer science a lot. So this basically tells the system, I'm ready to proceed, but it doesn't actually proceed until everybody else gets it. And BlackLine says, okay, we're all in lockstep, go. And so this is still work we're working on, because some systems are really faster, some are slower, and some don't care about real time, and how do you implement this in practice? But that's worked out. There's these delicate APIs, which really need different computer languages, and we've got them in C, C++, C#, and Python at this point. And then the router APIs are the ones that basically go, these bits and bytes emulate a star tracker, and you're a flight system, so this information has to go into these registers. It's very hardware specific and mission specific. That I can't give you a general interface. But we are doing it for different languages, so you have something you can go, and it translates across. This was a simulation I showed a year ago that we got running, and we got cleared to show. It's a very basic simulation. Spacecraft is dropped off the craft. These are the attitude coordinates. Optimistically, the students felt it wouldn't be tumbling, which I agree is a little bit optimistic. But the key thing is it has ground system built in. It's running actual flight code on an emulated chip, and it's tying in the physics from our Basilisk simulation. And so it comes off. Then ground, this is the green line. Ground says, okay, I get communication, go into acquisition mode. That means gather data, figure out where the sun is. Ground monitors that, and at some point you go, yep, I believe your answer. You're good now to start to fire up thrusters and point yourself at the sun, which you say here. So this signal gets sent across to the board, which sends thruster commands to here. And you're emulating a full-on mission operation, and now it orients itself the way it should and converges onto it. So this was a huge step to get this level of fidelity running within an open tool. Vizard, which is our visualization that we have here. We've gone through 3 different generations of this. If you have these massive simulations, you've got tons of data to debug. And then on a spacecraft, I remember this one student I had, Steve O'Keefe, he's now at the Lincoln Labs, brilliant guy. But he spent days trying to debug why his sun estimator wasn't working. He would put out, check all the code, check all the filters, check the algorithms, see how that stuff is going. He couldn't figure it out. And then finally, he used my visualization I created at the time, put it all in there, looked at it, and guess what was wrong? He was flying in the shadow of the planet. And the simulation was set up to give you shadows of planets. So of course, the core sun sensors were getting no signal, and that's why it wasn't working. And he was going, well, it's not being initialized. Why is it, it went through the init cycle. Why is it not getting anything? Well, because nothing was coming in. That's stuff that you can spend a lot of time trying to figure out, looking at all the wiggles and jiggles that happen in these plots. If you can get a 3-dimensional version of it, you will quickly put it in context and going, oh, wait, that's what's happening, So we're doing this, and we're trying to now use Unity, the gaming engine, because we can create all kinds of stuff with much nicer engineering-friendly tools. Like here we have a spacecraft model, firing off thrusters. We can use particle engines, so the thruster plumes are proportional to the force of the thruster. If you put the wrong, like here you see small attitude control thrusters. These are the big orbit insertion thrusters. If I put one of them here, it would be really visible very quickly. You've misconfigured the spacecraft. The other thing we do is you see a planet, Mars, that's cool, but it's not there because it looks cool. It's there because we're actually simulating the gravity of Mars. A design decision we made early on is we're not going to throw everything into the solar system that you get to play with. We're only showing you what you're simulating. If you don't see a sun, you're not simulating a sun. There's no sun heading, so therefore the core sun sets again wouldn't get a signal. If I see a moon, I have moon gravity turned on. If I don't see a moon, I don't have gravity turned on. So this becomes a quick feedback on very complex systems as to what is the physics that you're actually simulating. So that's cool. We're using this in the flat set where you have your hardware in the loop, your breadboards, everything laid out, and this always visualizes what's going on. That's been, at the beginning, Scott Pickett, the lead engineer for the ADCS on the mission, was like, well, that's kind of nice for demos, but now it's running day and night. He's always got this up because it always shows him what's going on in the full context. And it's integrated in there through the BlackLine architecture so he can tie it in with these other things that they have to do, the telemetry, the ground systems, and there's always messages being sped across to this visualization. So this gives you a 3D interface, but it's shown in a 2D way. This video, this was taken early summer. We've got a much smoother version. Andy did this for fun last year as a master student. He wanted to do VR, so we got a VR headset. Now we've been able to use Unity to export a VR version of it, which is pretty cool. At first I thought, well, it's not much money to get a VR headset, go for it. We'll see how many buckets of puke we'll generate by the end of the semester. Exactly. The answer was 0, actually. So far it's worked out really well and it's been interesting. So you can zoom, you can walk your way through, you can bring up the spacecraft, you can walk around it and get full three-dimensional context of where things are, lay things out. So we're still exploring how to make use of this for mission design. But I think we're not that far off to have Minority Report-like interfaces where you can bring all these things up, bring up the panels. I want to see this. No, show me these states. One of my students, she's done a lot of missions on Solar Probe B and other things, and she was telling me the stories, how many weeks she spent debugging some stuff. And so we want to find ways to give much better interfaces for debugging in this. And I think these VR sets could be there. Where are we going with this? I've got lots of students, but some high level, some question that came up today as well, is Basilisk is great at simulating a trajectory, an orbit, with algorithms, with sensor, with environments, whatever's going on. That's it. If you want to wrap trajectory optimization around it, it would be wrapped on the outside. We are actually looking at wrapping machine learning around it. Machine learning is huge. It's coming everywhere. There are amazing amounts of money being spent on that. And a lot of these tools are made available in Python. So we've now used Gym and there's some open libraries also in Python. We've been modifying them this year such that we can create, we can call Basilisk from within those learning parts. So you can then seed it, go through the learning process. And the things we want to learn is not how do I make a spacecraft rotate left? I know that. The thing we want to learn is should I rotate left? The higher level decision making, which are more binary constructs that these machine learning algorithms love to learn. So we would like to basically replace the humans that have all these flight books and rules, and if this is okay, then it's a go, no-go decision point with how can the spacecraft do this autonomously and bring costs down. Other things we're working on is that visualization I showed you is not just something that looks cool and do demos, but it actually becomes a visual sensor for us. We've got the hooks in place to where I can say, give me a camera image pretending it's a 1080p, 4K, 60 hertz, pointing from here with this focal length, and it will send back an image with the messaging system that gives me that. And then I can use OpenCV to corrupt it, to put in noise, to put in distortions, whatever. And now Thibault is running fully visual closed loop stuff simulations within that. That is huge, and we really think there's a lot of growth and potential there. But also we're adding things like power subsystems, data systems. This is coming often from mission design and industry where they're trying to figure this stuff out. How much time do I spend gathering data versus doing science versus communicating data? Because at some point your buffers, your memories are full. And that's a big challenge. The same thing with power management. So those are modules we're working on. There's a bunch of other things. I've got a whole slew of students working on this. But we're super excited about this. This was something I didn't think 5 years I'd be getting into. I've always loved software, so this gives me a chance, kind of a midlife crisis, to get astrodynamics and get its software. As an editor-in-chief, I can tell you, the journal definitely considers space software also as an emerging technology. Though the AAA does have a journal on aerospace information systems specific to software now too. But it really is growing up and what we can do. But we need modern techniques. We cannot keep flying 30-year-old code. We have to, as engineers, you guys need to learn how to code in teams, how to code massive projects. Because when you go out there, it's not going to be me, myself, and I working on a little sim. You're going to be integrated in a bigger community. So those are fantastic skills to do. And I think this is a step in the right direction for us. But with that, I'll be glad to take any questions or comments you might have. Thank you very much. Any questions? Yes, sir.
What do you feel Basilisk brings to the table as opposed to What do you feel Basilisk brings to the table as opposed to commercial software like AGI, Satellite Toolkit?
So SDK, up to a few years, didn't even know attitude dynamics. It was very closed. It was great for high-level mission. Where am I going to be? When can I communicate? Doing all this, some basic trajectory design and formations. Now it has some hooks to do some very basic satellite dynamics on the attitude side, but this does way more. The big thing, I think, is the thing we're doing with the GPU. The way you have access to this, you wouldn't be able to do in SDK directly. SDK has different purposes, and AGI's business model is not just the software, it's really the consulting and what you do with the stuff. When we looked at early tools too, we needed modularity. We need a way to take our algorithms and flow them directly. So with our approach, I don't have to auto-code. I'm already writing in C, but I'm testing it in a way that's much more, Python is very MATLAB-like, so it's more comfortable to students. And then nobody has to rewrite that code to go from analysis to hardware in the loop to actual mission testing. It's that whole workflow that we wanted to have. And for that, the message passing interface was critical because we need to know who touches data and who doesn't. And if something goes wrong, I can follow the chain and see that's where something happened. So that whole architecture we never had, you'd have to backfit it onto that. The other big thing is the open nature. If I'm doing research and SDK solves it, guess what? It's not research, it's production. It's already been done. I need to have really access to do the unreasonable things that SDK never even thought about. That's why it's research. And so we needed a TORs. The other close companion, I think, closer than SDK has different purposes, and it does those really, really well in what we're doing. Something that's closer is probably JPL's DShell and Darts and those software packages, but they're very JPL in-house. They're similar that they're compiled code wrapped in Python, and you can call them from Python and do some crazy dynamics, but that's kind of where the similarities end. And it's definitely closed, and we wanted something that's open, that we fully control. We're not depending on anybody else, because we had to use it for a mission as well. And if we just don't like something, I can go change it and make it specifically what I needed. So I think that's where this big design differences come. Thanks. There's a question back there, sir. Yep.
Hi. The message passing interface, kind of the core of your modular architecture. Message passing interface, or MPI,
was built more from the ground up with specific needs that we needed, with write access and control and tracking and so forth. So we use MPI, but that's a generic name. There is an MPI actual software, right? There's a platform on that for multiprocessing stuff too. That's not that MPI that we're using here. So ours was more built in. We try to use, so we're revisiting what we have with the messaging. It is super fast, but it's not very capable, but you get the speed. But that means the coding for it requires more stuff to be aware of. We're now trying to make it smarter. So if I write a message, that it will know which spacecraft wrote that star tracker message, instead of me having to track all that stuff and put that in there. And in other places, we switch to things like Google protobuffers, which is a way to do messaging that's highly serialized, and it's very smart. So if you get new features, you can run it. But there's a performance hit that comes with it that we were hesitant to go full on something really advanced like that. It had capabilities we just didn't need at the time. So it is a great question, because we started with one, we had to get running, and Scott ended up writing it from scratch. It's a really fast, highly particular to this, but now we're looking at it and going, okay, I think there's some features we would like to add, so we keep revisiting when do we do it ourselves and when do we just tie into things that have already existed there. So I think this fall we are redoing it in one way, but who knows, 2 years from now, it depends on the capabilities on those messaging systems. Yes. Yes, sir.
So you said how they were using code from 30 years ago. Do you expect this code to be used 35 years from now, or will you be working on the next variant by then?
Oh, God, man. I hope it's not used 30 years from now exactly as it is. It should have evolved. Because as always, I'm already looking at it and going, things we wrote 3-4 years ago, man, if I wrote that now, there's a cleaner way to do it. I've learned better ways to do it. You may have discovered other code people have solved this particular challenge already, and maybe I can integrate it better. So I really hope for this to be a dynamic, fluid kind of a framework that we can all contribute, expand, add capabilities, tie into other things like these machine learning libraries, or we're talking earlier about optimization libraries that might make use of it just as the engine that runs the simulation or something, So I hope for this to be much more fluid, not a static thing. But that's where you still have to have the built-in integration tests, unit tests, all the stuff, because otherwise you go, oh, I changed this, but what did I break that I never thought of? So it'll, yeah. I mean, but if you look at big software companies, that's exactly what they're doing. If Amazon, Apple's, Google's, Facebook's, all of them, they have massive code bases and they have all these tests that are running. That's how you write code these days. You don't just write code that goes, well, it ran on Thursday on my computer, but you write code that gets tested on different platforms, automated scripts, you know. So that's what we're trying to instill in our engineers. And if we do that, it would allow us to be way more flexible and continuously improve. That means this should be outdated and replaced with much better things. Newer, you know, Go, do we include Go from Google or Swift from Apple or who knows what languages come, all right? It shouldn't be this forever. Yes?
So yeah, I was wondering about how you went about taking, the difference between that interpretive part and the compiled part of your software. So the higher level of extractions that you get through Python and the lower level high performance stuff you get in C++. So how do you go about deciding when users should get that, usability features?
That was never an option. Because we don't fly MATLABs on spacecraft, you know, so we knew immediately that the algorithm needed to be in C, because that's what people typically are. We're going slowly towards C++. The next stuff, we probably would just fly C++ now. So that was one. We knew we wanted C++ because I want to do modern computing, at least with some object-oriented elements. So those went in. You can make modules in Python as well, which are slower, but if this is a module that gets executed, it simulates some communication that happens once every 10 seconds, it has a minimal impact on the total simulation time. And it's kind of like MATLAB Python, right? You can prototype it much quicker, so that would go there. From an internal side, we haven't done too much prototyping, like speed comparisons and which method would be quicker or faster. Scott got this up and running with this messaging system that we have. Again, it's a very bare bones, fast, you're close to the metal kind of a thing. And it's worked really well for us. So it got the mission, it got us the analysis that we needed. Now we're looking at it going, well, if I want to fly hundreds of satellites, this is going to be doable, but it's cumbersome. And we need more features in that messaging system. So we're revisiting that right now. Speed will be something we'll look at. We had that question, for example, I had my own C libraries for doing matrix math that were hand-coded very fast. We've switched over now in the simulation to use Intel's Eigen library. It's slower than my code, but it's much more general. It can solve things in way more general ways. But in debug mode, it's way slower. The trick was once you go into profile mode, a release mode to compile, it's pretty close then in speed, but still a little bit slower. But we felt the benefits there for an engineer to go in C code and do this vector plus this vector and the product times a matrix. It's so much nicer. It was worth it, So it's a little bit individual, but to me it's been a fascinating discussion we've been having in our group where we're bringing in computer scientists who have some ideas how you run it. You've got the engineers who are trying to use it in this ways and really figure out we want to have the right computer science tools we're bringing, but the audience is really an engineer who's trying to put down a mission, who doesn't have a computer science degree, One place we're talking about integrators. I can exchange different integrators, and this ends up using some computer science wizardry where they use polymorphism and other kind of stuff to make these things all work that most of my engineering students wouldn't know what they're talking about. But once it's done, the implementation, as an engineer, you don't have to understand that stuff under the hood. You just need to know, this is what an integrator does. Okay, I'm taking a 4th order, and I'm going to change math and make it an 8th order. And it then works, So those were those design decisions that we had to kind of play with, where I want to use, CS-like things, but make it usable to engineer. And that's always a balance, and the balance can vary from year to year. Good. Well, thank you very much for your time. I appreciate it. Small circles.